Hello, we continue our discussion of support vector machines and in particular the geometric margin. So we have seen that the aim of the SVM is to find margins and the largest gap margins so that the separation between the positive samples and the negative samples is the maximum. We are assuming a linear decision surface, and such samples which are closest to the decision surface are called the support vectors, and these also define the equation of the boundary. So they are very important for this classifier, and these are also the defining uh, samples for the decision boundary. So functional margin for a training example XI the functional margin of the decision surface defined by W and B with respect to XI is defined as follows. Now, for the set of examples, if we had say m examples, the functional margin for the entire set would be taken as the minimum overall the samples. However, we have seen that functional margins are not scale invariant. We can change the value of the functional margin by scaling the W's and B's as seen previously. And so we want to move on to the geometric margin. Now we consider this decision surface. We have the two types of examples. Now the vector W is orthogonal to the decision surface defined by W and B. Okay, this decision surface, this we can check the vector W if we take the vector W. Now to find the decision geometric margin, we take a sample X which is not on the surface and take its orthogonal projection on the decision surface and call it XP. Okay, and the geometric margin is which we want to find is gamma I. Okay, now when W is the vector orthogonal to the decision surface, then W by norm of W would be the unit vector in the same direction. Why we need this unit vector? We'll just now see. The geometric margin, the absolute value multiplied by the unit vector gives us a vector in the same direction of the length gamma I. So XP, the vector XP can be found in this manner. Xi minus this vector, right? We have this X vector, I'm sorry, it should have been a straight line. And then we have the this vector and subtracting them, we get the XP vector. Okay, vector X minus XP, we get this vector. So now one thing to be noted is XP lies on the decision surface. So it would satisfy this equation. So we substitute this value of XP in to this at the location of X, and when we substitute and solve, we get the equation for gamma I, which is very similar to that for functional margin, except that we have this division by the norm of W. And we can also see that if we have norm of W equal to 1, then there's no difference between the gamma I and gamma hat I, which was the functional margin. And as before, for the case of functional margins, for a set of examples, we define similarly geometric margin for the set of m examples as the minimum over all the samples. Right? Now, the support vectors, we again redefine the support vectors, which we have already seen as those which are closest to the decision line, decision surface, or in fact lying on the along the gutter line or the gaps. We see this is this and this is this. So those vectors which achieve this minimum distance. So this we had taken out the geometric margin for all these samples. Okay. So this is the minimum value. So on the positive side, and similarly we have the minimum value on the negative side. So these vectors which fall at that distance are called the support vectors. Okay. So as we can see now for this example, the decision surface which we found is this one. Which are the most important data samples? The support vectors. The entire SVM classification algorithm gives the importance to the support vectors because these define as to on which side the new data point would fall. These are the important data samples, the support vectors. Okay. Now, how we would actually find this decision boundary, or how we would state the optimization problem to find such a decision boundary, we'll very shortly see. Thank you. Thanks for watching.